Okay, so if you remember that in our first discussions of the adiabatic theorem, we had this classical example of a pendulum. And we had this pendulum, and as long as we move it around, we said that if we move it around slowly, its motion doesn't change. It just makes oscillations around this time-dependent fixed point, but the oscillation is kind of fixed. So that, and then we study the analog in quantum mechanics. Now, today we will start something that we call the geometric phase. It's a phase that will be that the wave function acquires due to a certain weird geometry of the problem. Now, we also have a classical analog of this one. Let's just imagine Earth. This is Earth. And let's assume that this is the North Pole, and we have a pendulum that is oscillating back and forth along this line. So it is oscillating along this line. Let's move this pendulum slowly. Then we reach the equator. Then let's assume that we move along the equator. And then let's assume we again adiabatically move back to the pole slowly. So this is the direction of the oscillation. Before it will be oscillating in this direction. After this full trip, it will be oscillating in this direction. So there will be an angle between these two oscillations. Although we came back to the initial point, the changing parameter is now back to the initial value. The state has acquired, it still has the same energy, the same amplitude, even classically, but now it is oscillating in a different plane. Okay. So this is the example we have. We have the Earth. Oops. Okay, we have, in this example, we have Earth, this is the equator, so we have this object, let's say in this direction first, it's the oscillation plane, then we move it over this big circle, and when it reaches here, it will be oscillating like this. So we move it along the equator, and then it will be moving perpendicular to the equator, and then we move it back to the pole, and now it moves in this angle. So there's an angle over here, this angle theta. Now we can relate this angle theta to all of this area. You see, if this is our area, the area will be equal to, well, half of the area of the hemisphere is 2 pi r squared. This is the half of the area. And then this angle is just theta out of 2 pi. So it's just theta over r squared. And so we can say that area theta is nothing but area over r squared. Well, this expression is nice because this is nothing but the solid angle of this region. So this derivation, although it will be a bit more complicated, whatever path you imagine, as long as it's a closed path, the angle theta will be equal to the solid angle. No matter how complicated or where it goes, whether it goes to the equator or not, it's not important. It will always be equal to the solid angle. Now, by the way, rather than writing it in this form, we can also say that, okay, there is a change, which is theta, and theta over A, this is equal to 1 over r squared. Did any one of you take general relativity or differential geometry? Topological. Well, this 1 over r squared is nothing but the curvature of this sphere. So in general relativity, what you do is, this is basically how you define the curvature of space. So you just take an object, a vector, basically, you just move it around a closed loop, and at the end of this closed loop, the vector changes a bit, and that change is proportional to the area, with the proportionality constant being the curvature of your space. So if your vector comes back to the initial vector after this closed loop, then we say that it is flat. If it doesn't come back to the initial point, then we say it is curved. So here, this is an example. This is written in this form. This tells me that the sphere is curved with a curvature given by the inverse radius. Now let's look at the analog of this one in quantum mechanics in adiabatic processes. So, question? Okay. So we had already seen that if, suppose we have a Hamiltonian, which of course it will depend on momentum and coordinates, but it will also depend on some parameters, let's call them lambda. If lambda depends on time, then our Hamiltonian will have a time dependence. And the solution of this lambda, we will have En, we will have the eigenstates psi n. They will be dependent on this parameter lambda, and this is equal to En psi n x lambda. And this equation, I mean, if you just replace lambda with its time-dependent function, the eigen equation will still be satisfied. So h pq lambda of t psi n x lambda of t, this will be equal to, well, the energy also depends on lambda, En lambda of t psi n x lambda of t. And so what else? And we usually have this notation, x lambda of t. This we will denote as psi n x of t. And we had proven the adiabatic theorem, which basically states that if our system starts in psi n x of t, it will stay in psi n x of t. Although even though we are changing lambda, it will be always in the nth state. The wave function will be different, the energy will be different, but nevertheless it will still be in the nth state. So that was the essence of the adiabatic theorem. So if you just have a parameter, let's say we have a state at t equal to 0. This is equal to psi n of x at t equal to 0. If we wait for some time, x at t will be equal to, according to the adiabatic theorem, it will be psi n x of t. Well, there is even if the parameter was time independent, there is a time dependence due to the energy. It will be, since this is an eigenstate, it will be just a phase. And now in this case, the energy depends on time also, so we get this integral minus I over h bar En of t prime dt prime from 0 to t prime. But there is still the possibility of having an additional phase. So the adiabatic theorem only tells us that the wave function will still be proportional to psi n. We have this energy dependence, but there is nothing that prevents it to acquire an additional phase. So just like in the example of the harmonic oscillator, it starts to make this angle. So of course it is changing in time due to its periodic oscillation. It is basically this the first exponential depending on the time t. Plus there will be this additional phase, which in the classical case amounts to the angle that it makes with the initial orientation. Now the question is, what is this gamma n of t? Are you following?
In our sphere case, or?
No, in general. I mean, that was an analog, and that is something to keep in mind. So in the sphere case, in the Earth case, the pendulum on the Earth, so basically this psi n of xt, in a sense, in the classical case, it will amount to the amplitude. The amplitude is fixed. The energy is fixed. Energy-dependent exponential is nothing but the time dependence of the oscillation in the classical case. But there's still the additional phase, which will amount to the rotation of this oscillation plane. So all of these terms have the classical analogs, let's say. But now we would like to find, in general, in the quantum mechanical sense, what is this additional phase? So that's our purpose now. And of course, we should also discuss, okay, there is this phase, can we measure it? Can we really define such a phase? Is it, I mean, in general, we say that the phases are not measurable quantities, so can we measure this phase? But first, let's see what that phase is, and then we will discuss whether we can measure it or not. Now, if this is, the adiabatic theorem basically states that this should be our solution at the time t. So this should satisfy the time-dependent Schrödinger equation. So let's just place it. So H acting on psi should be equal to IH bar d psi by dt. And so this H, of course, depends also on time t now, because our parameters depend on time t. So H psi, or H psi n, or let's write straight away. Now, H of t acting on psi n, our eigenstate, is nothing but my energy, En of psi n of x of t. There should be times these exponentials. That should be equal to, now I need to put the time derivatives, IH bar del psi n of xt by del t times the exponents plus En of t psi n of x and t times the exponents plus psi n times the first exponent times I, let's say, let me put a minus over here, so that when I multiply with the I, it just gives me 1. H bar and even put the H bar over there. D gamma n by dt times the other exponent. So this is our equation. So if that function satisfies the time-dependent Schrödinger equation, then gamma n should satisfy this equation over here. So we can just cancel, okay, the term on the left-hand side, cancel the second term. So we can cancel the exponents in all the terms also. And so we have this equation. IH bar del psi n x of t by del t plus psi n d gamma n by dt. This should be equal to 0. So let's just multiply both sides by psi n star xt, integrate over d cubed x over all of phase space or position space, whatever your space is. And then this would give you, well, it's properly normalized. Let's just assume it's normalized. So we have d gamma n by dt. This is equal to minus I h bar. Let me write it in this form, psi n d by dt psi n. Now we can do one more step, because you see the wave functions depend on time, but their dependence on time is only through the parameters. So if you just fix your parameters, then there is no dependence on time. So this is equal to minus I over h bar psi n. We can have more than one parameter. Psi n times d lambda I by dt. Or d gamma n is equal to minus I h bar psi n del over del lambda I psi n d lambda I. Or you can solve this equation by integrating both sides, and you would get gamma n of t would be equal to minus I h bar integral of psi n, the gradient, but with respect to lambda I. Psi n dot d lambda as a vector. So we might have many parameters changing, and lambda changing from lambda I, lambda at t equal to 0, to lambda at the time t, whatever that is. So this is our phase. Now if you come back, this was our wave function. Okay, this was the wave function we have. So we can just substitute it over here. This is psi n x of t e to power minus I over h bar from 0 to t e n of t prime dt prime. Well, h bars, they again cancel each other. E to power I times I, the integral of psi n gradient with respect to lambda I psi n dot d lambda. Now there are a couple of issues that we have to consider. If you note, I didn't multiply the i's. Because I mean, there can be a phase, but it should be a phase. That is e to the power some imaginary number multiplied with a real number. We cannot have e to the power a real number, because that would change the normalization, and the time dependence should be unitary. We cannot change the normalization. So we have to show that that matrix element over there, or that integral over there, is actually imaginary, pure imaginary, so that I times that pure imaginary number is a real number. Now let's look at that one. Psi n. We know that this is 1. It's just normalization. Whatever the value of lambda is, whether lambda is time dependent or not, it should be 1. So if you just take the derivative with respect to lambda I, you should get 0. So d by d lambda I of psi n plus psi n d by d lambda I psi n, this should be equal to 0. But the first term is nothing but psi n d by d lambda I psi n conjugate plus psi n d by d lambda I psi n. This should be equal to 0. So we are done. We have a number whose we take its complex conjugate and add to that number, which just gives me the real part of that number. So the real part of that number is 0. So this whole thing is twice the real part of psi n d by d lambda I psi n. This is equal to 0. Or that matrix element is pure imaginary. So that's why I keep that I over there. So if when I multiply I with that integral, what I obtain is a real number. Now let's imagine one more thing. So let's say we have our system here, or wherever you have your system, you are changing your parameters. You change your parameters such that you first, let's say, start from 0, it will finally reach a finite number, and then you go back to 0. So your initial Hamiltonian and your final Hamiltonian are identical. But nevertheless, this integral, this phase is still there. So you have this integral, psi n gradient with respect to your parameters, psi n, you integrate over your parameters over one full cycle that your parameters are changing. This is not necessarily 0. And this is what we call the Berry phase. It's just like the phase in the oscillator. In fact, if you do the quantum mechanical analog of the oscillator, you should get the classical thing. This will basically amount to that. Let's do an example of this Berry phase, or this phase in general. I mean, the thing is, you see, if you have a single parameter, then this phase will be 0. So you start, there's a single parameter, that parameter changes from 0, let's say an initial value to its initial value, and that phase will be 0. And in fact, there is one more thing that we can do. We can just use kind of the, I think it's the Stokes theorem on integrals. So this is, you can just think of this as a line integral over a closed path. We can convert a line integral to an area surface integral. So this thing is equal to I times some kind of a curl with respect to your parameters of this psi n dot dA. So if area goes to 0, this phase goes to 0. In a single parameter, you cannot have this Berry phase, but if you have more than one parameter, you can have this Berry phase. Now let's do an example of this phase, not necessarily the Berry phase, but we will just consider a single parameter. So the Berry phase will be 0. But there's, I mean, as long as you don't, your parameters do not come back to their initial values, so you will still get a phase. Let's do an example of it. Infinite well. Well, we had already solved it. Let's look at the ground state, or let's look at the general case. We have this infinite well, which is the length L. We already know what the solutions are. Psi n is nothing but square root of 2 over L sine n pi over Lx. So this is x is equal to 0, this is x is equal to L. And then we can imagine that L is a function of time. So as we are changing, as time goes on, the length of the well will be changing. So let's see, if you remember the definition of, let's just factor out the gamma, the i's, h bars, the gamma. This was equal to from 0 to t I times psi n del by del L psi n. This is our phase, dl. This is equal to I times from 0 to t, 0 to L initial to L final. L final dl. Then this matrix element is nothing but an integral over x from 0 to L. We have 2 over L. This is the normalization. And sine n pi over L times x times the derivative of this thing with respect to L. If you take the derivative with respect to L, you get n pi over L squared x with a minus sign and cosine dx. Now dx we already wrote. This is equal to, okay, dl. We have, let's see, minus 2 n pi over L cubed. No, not this. Let me take minus 2 over L squared. 0 to L dx sine n pi over Lx times n pi over Lx times cosine n pi over Lx. I will make a change of variable. I will just say n pi over Lx is equal to y. So that x is equal to L over n pi x, n pi y, and dx is equal to L over n pi dy. I times from L initial to L final, dl, minus 2 over L squared. Well, from dx we have L over n pi dy. Okay, if x is equal to 0, y is 0. If x is equal to L, y is n pi. We have sine of y times cosine of y times y. Hold on, we have a problem, no? What? Why should it be 0?
No, it's not periodic. No,
It's not periodic, because there is this y. There is another problem. Well, let's check the dimensions. So this L cancel this L. This is dimensionless, as it should be. The phase should be dimensionless. No problem with the dimensions.
It's independent of that.
Inside. Okay, fine. So what's the problem with that?
No, I just don't see that.
So we can just say that this is minus 2i times the logarithm of L final over L initial times whatever that integral is, 0 to n pi dy sine y cos y y.
Okay, what's the problem?
Is it real or imaginary? It shouldn't be. We proved that it has to be real. So how come?
This is all the ballpark of the expansion, right? We didn't skip an I or something.
No, not this one. Not this one. Not this case. You see the definition. Okay, let's go back. We said that this number, this matrix element, should be pure imaginary. Okay, that's something we said. Now we said that if that is pure imaginary, then this with that I over here, it is real. It should be real. Let's look at this example. I have this I, but you see the wave function is real. Its derivatives are real. So the matrix element is, it seems real. Why not? It seems to be pretty continuous to me. I mean, the cosine is a continuous function now. I'm taking the derivative with respect to the parameters. Now let's continue. Let's evaluate this integral. dy sine y cosine y times y. This is the integral we would like to calculate. So this will be equal to from 0 to n pi. This will be equal to from 0 to n pi dy times y over 2 times sine of 2y. This is equal to from 0 to n pi dy y over 2 times derivative with respect to y of cosine 2y over minus 2. Now I can do integration by parts. this will be equal to minus 1 over 4 times y times cosine 2y. Y is equal to 0 to n pi minus 0 to n pi dy cosine 2y. This is equal to minus 1 over 4. Well, what is cosine 2y when y is equal to n times pi? So it's, no, when y is 0, it's 0. So we have n times pi minus, that is sine 2y over 2 when y goes from 0 to n pi. That is 0. So this is 0. So we are left with minus n pi over 4.
No imaginary formation.
So we get the phase is equal to minus 2I times logarithm of L final divided by L initial times n pi over 4 minus n pi over 4. Which should be wrong. So what is wrong?
This is not due to the decay of wave function when we increase the length. Right?
There's no decay.
We took that part out.
Yes, either we made a mistake in the calculation or we made a mistake in the proof. Why? Okay, that's the hypothesis. So now how can we prove it? If there is a problem with the infinite potential. What might be the problem? I mean, you see, somehow if you claim that there is a problem with the infinite potential, it should invalidate at least one step in our proof. So that in the case of an infinite potential, the proof should not be valid. So which step do you think it invalidates? Well, I don't care about L equal to 0. I never take L is never 0.
X equals 2.
Okay, so where does in the proof does that come into the game? Yes, if you look at the general expression of gamma of the phase, okay, here we have the proof. This is how we evaluate that phase, and there we say that the only derivative we actually took is the derivative with respect to t. H, of course, contains the derivatives, but h psi n is E n psi n. That is how we define psi n, right? Okay, there's at least one step that has to be kind of not work in this case. I mean, if you remember the case when we studied... Oh, there is one mistake in our calculation, by the way. Where is it? Okay, now I see our mistake. I mean, I don't know if it will solve our problem, but there is one mistake in our derivation.
Zero, I suppose.
Hmm?
Like it is where you show it, right?
Yeah.
Yeah, there is also derivative of
The derivative of
Yeah,
normalization.
yes, normalization.
We did that. We
No.
took it.
I only took the derivative of sine.
I took it. I observed what you did, and I thought you took it. You took also the part.
No, like we took it.
You said 2n pi over l squared.
Okay, that is the derivative of sine with respect to L.
I think you take the total derivative, 2 over L's derivative, but we should take the.
I never took the derivative of square root of 2 over L.
Okay. I thought you took the derivative with respect to x, then there came n pi over l, and the derivative from l came as l squared.
You see, the derivative is with respect to L, not x. So let's see. Correction.
You were so sure while we were asking the problem. I was sure that there is something not wrong with our calculation. I think something physical or something that it should work in this case.
Well, you see, there is still the issue will still be open. Because the derivative with respect to 2 over L will just bring another fact, another real contribution.
But it might be zero.
Well, you see, it might be 0. You see, the wave function is real. Its matrix elements, even if you take the derivative with respect to L, should be real. But we proved that the matrix elements has to be pure imaginary.
If they are all zero.
And the only number that is both pure imaginary and real is 0. So the phase should be 0. But let's show it. So you see, okay, 2 from 0 to t, no, not from 0 to t. From L initial to L final, dl, dx from 0 to L of square root of 2 over L sine n pi over Lx times d over dl of square root of 2 over L sine n pi over L dx. This is what we should evaluate. So this is equal to from L initial to L final dl from 0 to L dx square root of 2 over L. Now let me just take the normalization of the derivative of the normalization. That will bring me a minus 1 over 2L times square root of 2 over L sine n pi over Lx plus the previous term. This is the additional piece we have. Now this is kind of easy to evaluate. This is I from L initial to L final dl of, well, if I take out this 1 over 2L out, what remains, okay, here I also have a sine n pi x. What remains is nothing but the normalization integral, which is just 1. The previous term was, let's see, we had evaluated it here. Plus this one. This is equal to minus I over 2 logarithm of L final over L initial plus n pi I over 2 logarithm of L final over L initial. So we apparently have a mistake in our previous calculation also. Let's look at over here. I have this 1 over n pi, 1 over n pi, over n pi, which I forgot. This n pi. So the final answer is 1 over n pi. So this n pi is not there. I over 2. This n pi is not there. This n pi is not there. So gamma n of t, this is equal to 0. So actually, if the wave function is real, we don't get any phase. The wave function has to be complex to get some phase. Yes, any questions?
If it was complex, can you measure it?
Can we measure this?
If it was zero.
Like, this is measured, but in a theoretical sense, right?
No, even in practical sense, it can be measured. Well, you see, if you just have a single wave function, of course you cannot measure the phase. Even the time dependence you cannot really measure. But you can get different, you see, these parameters can be changing in different regions. So I might have, let's say, I can be sending an electron beam over a double slit. And over a double slit, I will get this interference pattern. Right? So I can have some parameter changing in part of the space. That is, let's say, close to one of the slits. And there won't be any changing parameter close to the other slit. So basically, there will be this phase that only one of them acquires. Or even it might not be just a single one of them, but I can have parameter changing differently at different regions. So the electrons, the wave that goes through the above slit and through the below slit, they will gain different phases. So the interference pattern changes. And this is even experimentally measured. Now, one thing we will be discussing as an example on Friday will be the Aharonov-Bohm effect. Aharonov-Bohm effect, this experiment that I have been mentioning. So let me just mention what it is. The experiment is this one. Suppose you have this double slit. And you have a magnetic field over here. A solenoid that creates a magnetic field. Right, the Aharonov-Bohm effect is important in two things. One is it's a Baire phase. It's a kind of a Baire phase. So it's a geometrical phase. The interference pattern over here will depend on this P. And in fact, you can just put these slits sufficiently far away. And make sure that the solenoid over here have thick walls so that the electrons cannot even penetrate there. So you can make sure that the electrons will never see a non-zero magnetic field. But nevertheless, the interference pattern that you get on the screen will be modified due to this P. Because outside the vector potential is not zero. Although outside the magnetic field is zero, the vector potential is not. And somehow the electron feels the vector potential, not just the magnetic field itself. Still, the observables, the shifts in the interference pattern, will be proportional to the magnetic flux. In the solenoid, although the electrons do not enter any region which has a non-zero magnetic field. This is called the Aharonov-Bohm effect. This we will discuss on Friday.
But vector potential also
outside there's no electric field, there's no magnetic field, nothing.
So
Only in this case, if you have a solenoid, the scalar potential will also be zero. There will be only the vector potential, which is non-zero, and the electric field will be zero.
such a combination is possible.
Sure. You see, just imagine a solenoid. It creates a magnetic field, but it doesn't create an electric field. You can solve for the vector potential in magnetostatics. And there won't be any scalar potential.
Del cross A is 0.
Outside this solenoid.
No, at any point, del cross A is 0. Okay, I'm thinking about the whole thing, maybe at some point.
Well, you see, inside A shouldn't be zero, definitely, inside the solenoid. Outside the solenoid, well, the vector potential has to be continuous. So outside the solenoid, it also cannot be zero.
So if it has a divergence, the electric field is equal to
Just imagine.
potential plus gradient of divergence.
Just imagine a solenoid, a simple solenoid. That's the configuration we have. There won't be any scalar potential. Well, of course, depends on the gauge. You can choose a gauge in which has a scalar potential also. But the easiest choice will be zero scalar potential, non-zero vector potential. Anyway, that is for Friday.